Hello and welcome back to the Geodynamics video lectures on viscous deformation and the strength of the lithosphere. In this third lecture on the topic, we're going to take a look at the atomic scale deformation that gives us the two different types of viscous flow that we observe in rock, linear and nonlinear viscous flow. Basically what we're going to do is describe these two different types of viscous deformation at the atomic scale. So we'll look inside crystals to see what's happening that gives us linear and nonlinear viscous flow. The first type of deformation in a crystal that we'll talk about is called diffusion creep, and this results in linear viscous flow of materials based on diffusion creep at the atomic scale. The way it works essentially is that we have atoms diffusing through the crystals when they're stressed and jumping into vacancies in the crystal structure. So over here on the left side you can see a number of different letters, A and B, separated by a dashed line here, and you can see that this would be a regular grid of these letters, except there are some open spaces here. These are the vacancies. You could think about these being different atoms in the structure of a crystal lattice or whatever you please, but basically the idea is that there are some atoms that are in a place where they are content, and then there are some vacancies in there that will allow the atoms to move around within the crystal. And so when we talk about diffusion creep, we're talking about exactly that process, the migration of vacancies or migration of atoms into vacancies within a crystal. Now this can occur both in the interior of the grain, which is kind of like what we would be looking at here, and we'll take a look at a little bit more of what happens in this figure in just a moment. And it also happens at the boundaries of crystals, and as a result of the movement of atoms within the crystal structure, of course, that results in deformation to the crystals. It ultimately results in rock strain. And notably, this is something that occurs really only at very low stresses. So here, if we start with our picture in A, one thing you might not have noticed yet is that all of the letter A symbols here, this whatever atom A, are on the left side of this dashed line. Now, if we go some time later, we might expect that randomly these atoms A and B may have moved around within the crystal if there's enough energy for an atom to migrate into a vacancy. So for instance, here you can see where this arrow pointing to the left is where we had previously atom B sitting here, and it's moved over to the left into that vacancy. Same thing has happened with A moving to the right, or sorry, B rather moving to the right across the dashed line, a B here that moves over. You can see between A and B kind of what's gone on. And importantly, you can see that here we've had one atom of A move across the line into the area that was previously only occupied by atom B. Now, if you continue on doing this 4 times C and D, 2 times later, what you'll ultimately end up with is basically a homogeneous distribution of atoms A and B on both sides of this dashed lines. And this is basically how diffusion creep would work within a crystal. You could just replace atoms A and B with whatever elements the crystal is composed of. Now, this diffusion creep is can be sort of illustrated at a little bit larger scale here by considering a box that looks like this. So if we had some box of rock, of some crystal or rock initially that looked like this solid line here, and we squeezed from the 2 sides like is indicated here, and then stretched from the other sides, what would result is that because of the compression on the sides of this rock box, we would have migration of material from the face where you're having a compressive stress toward the area where there is a tensional stress. In other words, from faces A and C, we would see migration away and material moving toward faces B and D. And again, you can see clearly that in this case how this box of rock or this crystal would be getting more elongated as a result of the applied stresses. Now we can also consider dislocation creep. And dislocation creep is a bit of a different beast. In this case, what we're going to look at are two different kinds of dislocations in the crystal. And in this instance, instead of migrating atoms and vacancies, we're going to have imperfections in the crystal structure that are going to be migrating, and these are called dislocations. And the net behavior for this kind of deformation is something like power law flow. Now there are basically two different kinds of dislocations, edge dislocations and screw dislocations. What you can see on the left side of the slide here is an example of a diagram of an edge dislocation. Maybe not so easy to tell exactly what we're looking at, but in this case you can imagine we're looking at the side of some crystal with a regular lattice of elements that are forming the structure of the crystal. And so you can see down here a very regular grid of points. And if you were to start, for instance, here at this position within the crystal lattice and move 3 over, 2 down, 3 back over, and 2 up, you would have moved a total of 10 atom distances or spots around in the crystal lattice and come back to your original starting point. Now where we have this edge dislocation, we basically have an extra set of atoms in the structure. And in this case, you can see that by moving 3 atoms over, 2 down, 3 atoms over, and 2 up, we don't return to the original starting spot, but we still have 1 extra vacancy or at 1 extra point that we would have to move to in order to go back to our original starting place. In other words, the circuit that we've gone around is not the same length as it was before, and that's because basically we have an additional plane of atoms that are stuck or kind of wedged into this crystal lattice. And so that was the example of an edge dislocation. You could think about that as a plane of atoms that just kind of forced its way or is stuck in the crystal lattice and resulting in strain within the crystal. A screw dislocation is the other kind of dislocation in a crystal structure, and the figure is kind of shown here for what a screw dislocation would look like. In this case, we would have atoms that are in and out of the plane of this crystal lattice. So if we're looking down, for instance, on the top plane of the crystal, there would be some atoms that are basically sticking up above that plane, such that if you start at position 1, at this atom here, and go 1 down, 3 over, 2 up, 3 over, and try to go 1 down again, instead of coming back to the atom you started from, again, you end up in a different position. In this case, you'd be 1 level higher in terms of the planes of atoms in this crystal lattice. And so that is your screw dislocation, because now you're 1 plane higher than you started, and you'd have to then move down by 1 lattice spot to go back to your original starting atom. And if you were to go and do the same thing elsewhere in the crystal where there is no screw dislocation, you should come back to where you started based on this kind of simple method of walking around the crystal structure, stepping from atom to atom in the lattice. Okay, so now we have our linear and nonlinear viscous flow. We've talked a little bit about kind of how this works in the crystal scale, and it's time again to take your quiz. And when you come back, we're going to start putting things together and talk about the strength of the lithosphere.